Hey everyone, welcome back to Linear Algebra. This will be part B of lecture 5. And where we left off, we had just introduced the row operations that are used to complete the Gaussian elimination process. So row operations. Let's quickly review those just to get them front and center in our mind, and then we'll discuss the overall strategy of Gaussian elimination. So the first row operation was to multiply a row by a non-zero scalar. Okay. The second was adding a scalar multiple of one row to another. Adding a scalar multiple of one row to another. And then the third row operation was switching the position of two rows. Okay, switching the position of two rows. Okay. And so there's a general strategy that we want to adhere to, and the strategy is going to revolve around what are called pivots. Okay, and so the pivot, like in the strictest sense, you'll recall that we had our matrix operations, and we said there's going to be all this hard stuff, but in the end, what we hope to get to is something like this. Okay, something like this, where we have kind of a diagonal matrix or maybe an upper triangular matrix. But we've reduced a lot of the entries in the coefficient matrix to 0, but retained some non-zero entries. Those non-zero entries that are going to hopefully fall on the diagonal, these are what we mean by the pivots. Okay, so these are the diagonal entries in our we'll say reduced augmented matrix. Now, ideally, these pivots have the value of 1. Although that's not strictly necessary for Gaussian elimination. Okay, but 1 is the easiest to work with for these pivots. And so this is what we mean, though, by the word pivot. So it's going to be these diagonal entries in the reduced matrix. Okay, so let's discuss our strategy overall here. How do we want to go about this? How do we go about applying those row operations to that initial matrix and step by step converting it into this reduced matrix? Okay, so there's it's pretty straightforward. It takes a second to learn it, and then a few examples to get the hang of it. But here's the basic strategy. So you want to start by getting a pivot in the first row and column. So I'm going to start by getting a pivot in the first row and column of the matrix. Right? And so how do we do that? How do we get a pivot in the first row and column of a matrix? Well, it's always done the same way. It's either row operation number 1 or sometimes, in lucky cases, row operation number 3. So we'll want to use row op number 1 or number 3. Okay, and so at the end of step 1, our augmented matrix should look like this. You'll have a 1 here, and who knows what elsewhere. It doesn't matter, right? You'll get a 1 here, and then everything else is unaffected at this point still. Okay, and how would you do this? Well, let's say, for example, this first row, first column value was a 2. Well, all you'd have to do is use row operation number 1, multiply the whole row by 1/2, right? And then 2 times 1/2 is 1. Okay. Or if you're lucky and one of the other rows in the matrix has a 1 as its first column entry, you can just switch the rows. That's row operation number 3. You can just switch rows. Switch the rows around. Put your 1 up here. Get a 1 here. Okay. So that's the opening move in this strategy. All right. Now step 2 then is to use, so now you have a pivot. This is what's called a pivot, right? We just defined that. Okay. And so you want to use the pivot to convert all of the entries below it to 0. Okay, so you want to use the pivot to convert all entries below the pivot to 0. Okay, and so that means you'll have a 1 and then 0, 0, we'll say 0, okay? It doesn't really, we don't know how many rows are in here, but this is just a schematic so you can kind of see the idea. So you convert everything below the 1 to 0, everything below the pivot to 0. How are you going to do that? What row operation will enable you to do that? Well, that's going to be row operation number 2. Okay, and so that's real easy, right? Let's say I've got my pivot 1 here. Let's say this entry below, which is written as 0 here, let's say instead it started as a 5, right? Well, all I have to do to convert this to a 0 is to multiply my pivot by -5 and add it to this. So if I have a 5 here, I multiply the pivot row by -5, and then I'm going to have what? -5 plus 5 makes a 0. And I don't care about what happens over here yet. I'm not worried about that. I'm just worrying about get the 1, then get all the zeros. Okay? That's the idea, and that's always going to be used. You're always going to use row operation number 2 to create zeros. Row operation number 1 is how you get your pivots. Row operation number 2 is how you get your zeros. And number 3 can be helpful with getting pivots mostly. Not super helpful in other cases usually. All right. Well, that's step 1 and step 2. What comes next? Well, step 3 then is to get a pivot in column and row number 2. Okay, so what does that mean? Well, remember what we have so far. We've got a 1, and then we've cleared out everything below that pivot. What we want to do next is we want to say, okay, let's move over to the next column, but we're not going to worry about what's happening here. Instead, we're going to look at, we're in the second column, so we want to look at the second row. So what we want to do is get a pivot here. Okay, and everything else doesn't matter at this point. Get a pivot in row 2, column 2. And again, we're going to use row operation 1. Okay. And then step 4, you're going to want to use your new pivot to get all 0 entries below it. Okay, and so here's what we're looking at. You got a 1, 0, 0, 0 in the first column, and now you've got a 1 in row 2, column 2. You want to get zeros below it. Okay, and then you want to continue. So continue moving right and down. So down and to the right. Right, until basically your matrix looks like this. So don't worry about that. So we don't know what numbers are up here, and we don't know what numbers are over here. We don't care as long as we kind of get what we're angling for is this upper triangular shape to the coefficient matrix. So we want all zeros below the pivots. Okay. All right, so in the end, right at the end of this strategy, in the end, the matrix will look like your matrix will look like basically ones on the diagonals, zeros everywhere else below the diagonal, and then you're going to have your scalar section over here, which is going to have some numbers in it, and then you're going to have the upper section of the coefficient matrix, which is going to have some numbers in it as well. So you're going to have ones on the diagonal, that's the key, and all zeros below the diagonal. Okay, ones on the diagonal, zeros below the diagonal. Okay, and when you've done this to the matrix, this is what we mean by Gaussian elimination. Okay, so this performing this on the matrix is what we mean by running a Gaussian elimination. Okay, and then what will happen is we'll be able to use this augmented matrix to quickly identify the solution to the matrix. And we'll get into that in a moment. Right now we kind of want to focus on how do we get the matrix into this form. So let's do a few examples of kind of running this strategy. All right, so let's start with a matrix and do an example here. So let's solve the system. Okay, and the system is going to be 3x plus y equals -5, -6x minus 2y equals 10, and 4x plus 5y equals 8. So here's our system. We want to solve the system using Gaussian elimination. Okay, and so let's go ahead and start by writing out the augmented matrix. So 3, 1, -5, -6, -2, 10, 4, 5, and 8. All right, so here's our augmented matrix. Now the first thing we want to do is we want to get remember step 1 is to get a pivot for the A11 entry. We'd like to turn this into a 1, right? And you can kind of look below and see, okay, neither of these are 1, so I can't just switch rows. I'm going to have to actually, I'm going to have to actually use a row operation of multiplying by a scalar. Okay, so step 1 is to get a pivot in the A11 entry. And to do that, all we have to do is multiply that row by 1/3. Multiply row 1 by 1/3. Okay. So we can easily do that. And the way I notate it is I just put a 1/3 next to that row, right? And so I know what that means. So row 2 and row 3 are unaffected. I just rewrite those in quick. All right, you're just changing row 1, and so 1/3 times 3 is 1. 1/3 times 1 is 1/3, and 1/3 times -5 is -5/3. Okay, so there we go. Step 1. All right. What do we need to do next? What's step 2? Step 2 is to get all zeros below the pivot. So now we've got this pivot. We want to turn the numbers below it into zeros. So step 2 is to get all zeros below the pivot. And so what does that mean? In this case, it means convert A21 and A21, A21 and A31 to zeros. Okay. Now how are we going to do that? How are we going to make this a 0? Well, I've got a 1 right above it, right? So I'm going to use row operation 2. Right? And what I'm going to do, have to do it twice. So the first time I'm going to do is I'm going to multiply row 1 by 6 and then add it to row 2. So that'll be positive 6 plus negative 6, and that'll make that a 0, won't it? So you can write that down. You can say 6 times row 1 plus row 2. That's going to be my new row 2. How am I going to make this 4 into a 0? Well, I'm going to do something real similar, but instead of multiplying by 6, I'm going to multiply by negative 4. So I'm going to take negative 4 times 1 plus 4. Right? So I'm going to go negative 4 times row 1 plus row 3. That becomes my new row 3. That's what I'm going to do to convert these two values to 0. Now, obviously, that's going to impact all of these numbers as well, but I don't care about that right now. I'm just going to keep just do the bookkeeping, keep track of it, and it'll all work out in the end. Okay, and so that's what we're going to do next. And so we'll start with the 6. So first we'll go 6 times row 1, and I'm going to add that to row 2. Okay, and so we'll write it like this. And so in this step, row 1 and row 3 are unaffected. So I'll write those in here. 1, 1/3, negative 5/3, and then 4, 5, 8. And then that middle row is what's going to change here. So 6 times 1 is 6, plus negative 6 is 0. And then 6 times 1/3 is 2, plus negative 2. 6 times 1/3 is 6/3, which is 2, plus negative 2 is another 0. Okay. And then 6 times negative 5/3 is negative 30 over 3, which is negative 10. And so that gives me negative 10 plus 10, which is another 0. Okay, so it looks like doing that row operation actually converted the entire row to 0. Don't worry about that. You only care about what's going on here. Don't look ahead and worry. Just worry about what's happening in column 1. Next, I need to convert the 4 to 0. So I'm going to multiply by negative 4, and I'm going to add that to row 3. Okay, and so remember, row 1 and row 2 are unaffected in this one. So let's rewrite those. Okay, so negative 4 times 1 is negative 4, plus 4 is 0. Then I've got negative 4 times 1/3 is negative 4/3, plus 5. So I'm just going to write that in here, and we'll simplify in a second. If you can't simplify it in your head, just write it into the matrix and come back to it. And then negative 4 times negative 5/3, that's 20 over 3, plus 8. Right, so negative 4 times 5/3 plus 8. Okay, and we'll come back to this. Let's go ahead and simplify this. So 1, 1/3, negative 5/3, 0, 0, 0, 0. Now what is this? Negative 4/3 plus 5. So that's like negative 4 plus 15, isn't it? All over 3, and so I get a negative 11/3 there. And then 20 over 3 plus 8, that's like 20 plus 24 over 3, so that gets me a 44 over 3. Okay, so you can't do those in your head. Maybe you can, just be careful, right? So a lot of times people make mistakes with this. It's because, they try to add too quickly. All right. And very good. So now we've got a 1, a 0, and a 0. Okay. So what comes next? Well, what I'm going to do next is I'm going to, so the next step, step 3, then would be to get a pivot in this position here. And so that's a 0 right now. And so what I can do is I can switch the rows here, row 3 and row 2. So let's do that. So I've got 1, 1/3, -5/6, and then I've got 0, -11/3, 44/3, and then 0, 0, 0 underneath. Okay, and so let me write this in step 3 here. Get a pivot in the second row and second column. Okay, and so in this case, well, whenever I'm trying to get pivots, the only way to do it is to multiply by a scalar, right? So in this case, I'm going to multiply by -3/11, aren't I? Just multiply by the reciprocal there. Right, that'll make this a 1, and this will be 44 over -11. So let's go ahead and switch pages. I'll just kind of do it like this. And so 1 and 3 are unaffected, so let's write those in. 6th. That should be a 5/3. Sorry about that typo. I don't know where the 6 came from. Okay. -5/3, and then this will be 0, 0, 0 on the bottom. And so what I have here is I have 0, and then -11/3 times -3/11 is 1, and then 44 over 3 times -3/11 is -4. Okay, and so that's our augmented matrix. Now, what you can see here is, and then the next step, we would continue on, we would try to get all zeros below this pivot. Well, we've already got a 0 there under this pivot, and so technically we are done, right? So we are done with row operations at this point, right? We've got our pivots on the diagonal, and everything below the pivots is 0. Okay. All right. Okay. And so that's the process. That's the process of using row operations to get to your reduced matrix. This is a reduced matrix, not a full. You could reduce it more, but this has been reduced. And so the solution set of this matrix is going to be the same as the solution set of the original matrix. The solution set of this matrix, and by this I mean this guy right here, is the same as the solution set of the original matrix. And what was that original matrix, just for reference? So it was 3, 1, -5, -6, -2, 10, and 4, 5, 8. Okay, so this guy here has the same solution set as this guy here. Okay, so this is the original matrix here. Okay, so how do we extract the solution set from what we're seeing here? Well, so how to extract the solution from this final matrix. How do we do that? Well, what we do is, in the case of Gaussian elimination, what we can do is we can re-express the solution, we can re-express the linear system, we can re-express the system in sort of the system notation. right? So we can take this thing and we can convert it back into a system. And so when we do that, we know that this is the x1 coefficients, these are the x2 coefficients, and these are the scalars. And so we can see that this corresponds to x1 plus 1/3 x2 equals negative 5/3. That's equation 1. And equation 2 is just 0x1 plus x2 equals negative 4. And then the third equation is all zeros, so we don't even have to think about it. Okay. And so our system kind of reduces down into this guy here. Okay. And I think technically I should write 0 equals 0, right? Because you do want to have the same number of equations, obviously, coming out of your augmented matrix in the end. All right, so a couple of things to notice here about this. The first thing to notice is that the third equation is always satisfied. Right? Obviously, because 0 equals 0, right? It doesn't matter what x and x1, x2, x3 are. Anything you plug in is going to be multiplied with 0, and it's going to equal 0. Okay, so it's always satisfied. Okay. Second thing to note is the second equation basically tells us what our value of y is. Actually, I'm sorry, I used x and y here. The original equations used x and y as well. Okay, so x plus 1/3 y equals negative 5/3, and then y equals negative 4. The second equation tells us the value of y. It tells us that y is equal to negative 4. Okay. And then how can we figure out what x is equal to then? Well, it's very easy, right? We know what y is. We can just plug that in there, and then that's called back substituting to figure out what x is. We can back substitute y equals negative 4 to get x. Okay, and so let's do that. So you have x plus 1/3 y equals negative 5/3. Okay, and so I know what y is, so that means x plus 1/3 times negative 4 equals negative 5/3. And so that means x is equal to negative 5/3 plus 4/3, which is negative 1/3. Yep. Okay. Oh, actually, that should be negative there. So to actually get negative 9/3, which is negative 3. Okay. And so our solution here is that xy is equal to negative 3 comma negative 4. Okay. All right. It's possible I made a typo in there, so double check that. But that's the idea, right? So once you get the matrix reduced down into this structure here, then you're reducing the variables as you move up, right? So this top equation could have all the variables still in it. The equation below that should have one fewer variables. Equation below that should have one fewer yet, and so on and so forth. Right? If it's a large system, maybe you've got 5 or 6 variables, you may have to have 5 or 6 rows to get all of the variables out of the lowest equations, right? And then you could just step back through the equations to systematically identify what each of the values are. Okay. Excellent. All right, let's do another example here of solving a system. Okay, and so that previous system had a unique solution we saw, right? Let's solve this one next. Okay, let's take a look at this next one. All right, let's solve the system. So so 3x1 minus 6x2 plus 3x4 equals 9. Negative 2x1 plus 4x2 plus 2x3 minus x4 equals negative 11. And 4x1 minus 8x2 plus 6x3 plus 7x4 equals negative 5. Okay, so let's take a look at this one. See if we can solve this guy. Okay, so first thing we have to do is convert this into an augmented matrix. And so we get 3, negative 6, 0, 3, 9, and then negative 2, 4, 2, negative 1, negative 11, and then 4, negative 8, 6, 7, negative 5. Okay, so there's our matrix. Step 1, get a pivot up here. How do we do it? Multiply by a third. Okay, and so we get 1 and negative 2, 0, 1, and 3. All these other rows are unaffected. Okay. Step 2 is to get zeros below the pivot. So we need to convert these two to zeros. Well, I can multiply row 1 by 2 and then add that to row 2 to turn that into a 0. I can also multiply row 1 by negative 4 and add that to row 3 to turn that into a 0. Okay, so I'm just going to do that in the next step. Okay, and so row 1 is unaffected. 1, negative 2, 0, 1, 3. And so what happens as I do this? So 2 times 1 is 2 plus negative 2 is 0. 2 times negative 2 is negative 4 plus 4 is 0. Okay, and then here I'm going to get a 2. Here I'm going to get a 1. And then 2 times 3 is 6 plus negative 11 is negative 5. Okay, so there's the new row 2. I can do the same thing for row 3. Negative 4 times 1 is negative 4 plus 4 is 0. And then I can go negative 4 times negative 2 is 8 plus negative 8 is 0. Okay, and then I'll get a 6 here, and then I'll get a 3 here, and then negative 4 times 3 is negative 12 plus negative 5. I'll get a negative 17 here. Okay, perfect. All right. And next up would be to get a pivot here, but there's a 0 here, so I can't get a pivot if you've got a 0, right? So now I have to move over to this one. So remember, you're trying to create this step down structure, right? And so if I can't get a pivot here, then I move over and try to get the pivot here. So this will be my pivot now. So I'm going to multiply row 2 by a half. And I get 1, negative 2, 0, 1, 3. These are all staying the same. So 0, 0, 6, 3, negative 17. And then here I'd have 0, 0, 1, and then 1 half, and then negative 5 halves. Okay. All right. So let's get a pivot. Let's get a 0 below the pivot here. And so that means negative 6 times row 2 added to row 3, right? And when we do that, what do we get? Well, we've got 1, negative 2, 0, 1, 3 at the top. And we've got 0, 0, 1, 1 half, negative 5 halves in row 2. And then I've got a 0, 0, and then here I get negative 6 times 1 is negative 6 plus 6 is 0. And then here you'll see negative 6 times a half is negative 3 plus 3 is another 0. And then this last one, this is going to be negative 6 times negative 5 halves, so that's 30 over 2. Yeah, so let's write this out. 30 over 2 minus 17. Okay. And what do I get? So this is just the thing I said, couldn't do that in my head. So this is going to be like 34 over 2, right? So what I can get here is 1, negative 2, 0, 1, 3, 0, 0, 1, 1 half, negative 5 halves, and then 0, 0, 0, 0, and then what is this? Well, this is 30 over 2, so that's 15 minus 17, right? So negative 2. Okay. All right, so I've got my matrix has now been reduced. Now notice I still have my pivots, and even though I don't have a pivot in every row on the diagonal, sometimes that can't be done, right? So some systems won't allow you to do that, and that's the case here. So at this point, I want to take the augmented matrix and convert it back into the normal system notation that we're used to. Okay, and so that means I have x1 minus 2x2 plus x4 equals 3. And I have, that's row 1, and then row 2's x3 plus 1 half x4 equals negative 5 halves. And then row 3 is 0 equals negative 2. Okay, and so that's the system that I'm left with after I do all the reduction to the matrix. Now, obviously, we've got an issue here with this equation 3. So notice, right, this equation is never satisfied for any values, right? So notice equation 3 is never satisfied for any values of x1, x2, x3, x4. There's no way to make 0, 0, 0 times something plus 0 times something plus 0 times something plus 0 times something equal negative 2. Right, so what this is basically saying is this is 0x1 plus 0x2 plus 0x3 plus 0x4 equals negative 2. Are there any values of x1 through x4 that can satisfy this? No, right? This can only ever equal 0. Right, and so what does that mean? Well, what it means is that this equation has no solution. There's nothing that can ever satisfy this particular equation, and what that implies then is that the system has no solution. Okay, so let's write that down. Right, so this equation, 0 equals negative 2, has no solution. Right, and when I say 0 equals negative 2, let me just make sure that that's clear. 0x1 plus 0x2 plus 0x3 plus 0x4 equals negative 2. That's really what we're talking about. Right, so that equation has no solution, and therefore the system has no solution. Right, the system has no solution. Right, remember, any solution to the system is going to have to satisfy all of the equations in the system. So if I've got this equation which I can't satisfy with any number, with any 4 tuple, then I can't have a solution to the system. Okay, and that's the situation. So this system is inconsistent. Okay, it has no solution. Right? There is no n-tuple or 4-tuple in this case that satisfies all three of these equations. Okay, particularly that last equation is the problem. Okay. All right, very good. Let's do one more, and I'm going to abbreviate this one because I just want to show you what it looks like when you have infinite solutions. Okay, so let's say we want to solve the system. Okay, so, and I'm going to actually just go straight to the augmented matrix, and you'll just know this is an x1, x2, x3, x4 system. Right, and so the augmented matrix looks like this: 3, 1, 7, 2, 13, 3, 1, 7, 2, 13, 2, negative 4, 14, negative 1, negative 10, 5, 11, negative 7, 8, and 59, and 2, 5, negative 4, negative 3, and 39. Okay, so when there's a system, you can convert it into this augmented form really quickly. But rather than write the whole system out, just in the interest of time. Okay, and so you're going to go through the operation here of converting using the Gaussian elimination algorithm. You're going to go through and you're going to get a pivot, then get all zeros, move over, get another pivot, then get all zeros, move over, etc. Right? So you can go through that whole operation. And what you'll find out is that this matrix is equivalent to this guy: 1, 1/3, 7/3, 2/3, and 13/3. Okay, and then 0, 1, negative 2, 1/2, and 4. Okay, and 0, 0, 0, 1, and negative 2, and then all zeros at the bottom. Okay, and so this system can be reduced down to something that looks like this. Again, just using the same operations. The only reason I'm not going through it in detail is just because it'll take 10 or 15 minutes, maybe 10 minutes, and we need to keep moving. So then this system can be converted back to its original format. So convert back to original format, right? And then when we do that, what do we have? Well, we've got x1 plus 1/3 x2 plus 7/3 x3 plus 2/3 x4 plus 13 over 3. Okay, and then I've got what? Well, I've got x2 minus 2x3 plus 1/2 x4 equals 4, right? And that's that one. And then this guy, I've just got x4 equals negative 2, and then 0 equals 0. Okay, so we just need to kind of get to this so we can reason about what's going on here. So a couple things to notice here. Okay, a couple things to notice. First, the last equation basically gives us no information about the solution space. So it's always satisfied. It doesn't care what x1, x2, x3, or 4 is. It's always just 0 equals 0. So that last equation isn't helpful. The third equation tells us x4 equals negative 2. Okay. Right, it tells us that x4 is equal to negative 2, but notice the values of the other three variables, x1, x2, x3, they're not uniquely determined, apparently, right? So they're all zeros, so the coefficients are 0 on that, so it doesn't really matter what they are. But x4 has to be negative 2. So the other three variables do not matter to this equation. Okay, and so let's talk through that a little bit more. What does that mean? Okay. does that mean? Actually, I'll do it this way. So what does that mean? So to see this, let's take a look at this. Okay, so to see this, let's let x3 take on any value whatsoever. Okay, so to see this, let's let x3 take on any value whatsoever. And the other three variables of the other three variables not uniquely determined, there are infinitely many solutions. Okay. Okay, so let's just do for example. For example, let's let x3 equal 5. Okay, I need to rewrite this. Okay, here's the system. Let's see it up here. For example, if we let x3 equal 5. Okay, if x3 is equal to 5, right, we can substitute. Sorry, we could starting with this equation, we can substitute x3 equals 5 in here, and we know that x4 is equal to -2, and that's going to tell us what x2 is. And we can then substitute that back in, those three values back into the top equation to figure out what x1 is. Right? So if x3 is equal to 5, then you have x2 minus 2 times 5 plus 1/2 times -2 equals 4. Now what is that? What is that equation? Well, that's just our x2 here, isn't it? x2 minus 2 times x3. x3 is 5, so times 5, plus 1/2 x4. We know x4 is equal to -2. Right, so we can just start plugging those things in. Okay, and so what does that imply? Well, it implies that x2 is equal to 4 plus 1 plus 10, so 15. Okay, and then plugging all of those values into our first equation, we can figure out what x1 is equal to. Okay, and so for that one, we get x1 plus 1/3 times x2, which we just found to be 15, plus 7/3 times x3, which we denoted as 5, plus 2/3 times x2, which is -2, which is equal to 13/3. Okay. And, you know, if you go through the arithmetic of all this, what do you find out? Well, you find out that x1 is equal to 13/3 minus, and this is just 5, minus, and this is 35/3, plus 4/3. And so we can do this quickly. 13 minus 15 minus 35 plus 4 all over 3 is -33/3, which is -11. Okay. And so a particular solution has been found. So a particular solution is x1, x2, x3, x4 equals -11, 15, 5, and -2. That's a particular solution. Right? But remember, all of this so this guy is fixed at -2, but these three values, they all came from our choice of x3. Right? If I choose a different x3, then I'm going to get a different x3, x2, and x1. Right? So if I plug in 10, for example, well, then all of this is going to unwind differently. If I plug in 1,000 for x3, I'm going to get, again, -2 here, but 1,000, and then these two will be different. Right? So in each case, the particular solution is dictated by the chosen value of x3. So there are infinitely many solutions. There are infinitely many solutions to this particular system, to this system. Okay, very good. So you can kind of see why that's the case, but how can we express the complete solution set? Is there a way to quickly express the solution set? How to express the complete solution set, right? Obviously, we can't like write them all down. There's infinitely many of them. But is there some way to denote them or to identify the structure of them? Yes, so we'll let x4 equal -2 as dictated by the matrix. Right, remember the matrix. What did the matrix show us? It shows us that x4 is equal to -2 if you look back. All right, so that one is always there. We'll let x3 equal some value c. Okay. Then x2 minus x2 minus 2c plus 1/2 times -2 is equal to 4. Just plugging -2 and c into equation number 2. That's going to imply that x2 is equal to 4 plus 1 plus 2c, which is 5 plus 2c. Okay. And then you can plug all of that into the first equation, x1 plus 1/3 times 5 plus 2c plus 7/3 c plus 2/3 times -2 is all equal to 13/3. Right, and you can do the arithmetic on that, but what you'll find out there is that x1 is equal to 4 minus 3c. Right, so I've got c, 5 plus 2c, and 4 minus 3c. And then x4 is -2. And so the entire set can be expressed, the infinite solution set can be expressed using just these kinds of statements. The infinite solution set is just, right, you could write it like this. It's a set, and the first component of the tuple is 4 minus 3c. The second component of the tuple is 5 plus 2c. The third component is c, that's x3, and then your x4 is always -2, right? Such that c is a real number, right? Any real number you choose will spit out a particular solution. All right. Okay, so that is that. Okay, all right, and you could spend more time. I recommend practicing that a few more times. It's not the hardest thing in the world, but it can be a little bit tricky. Okay. In fact, let's see where we at. Yeah, we're at 2 hours now. So let's. I want to wrap up with. Let's see. Actually, what I think I want to spend just a moment talking through. I want to spend a moment talking through how to derive this infinite solution set, and then we'll end after that. So let's do an example here. Kind of talk this through systematically because it can be a little tricky. I want to make sure that this is clear. So let's suppose that the final matrix after a Gaussian elimination is this guy. So this is kind of a bigger matrix. 1, -2, 0, 3, 5, -1, 1, 5, -1, 1. Okay, let's say I've got a pivot here, and followed by 4, 23, 0, and -9. And then I've got a pivot way over here, 1 and 16, and then everything else is 0. Okay, so this is my augmented matrix after I have gone through the Gaussian elimination process. Okay, so I've got my pivots and I've got my matrix structure is upper triangular. And here's what I've got. Okay, so this all can be converted into the system x1 minus 2x2 plus 3x4 plus 5x5 minus x6 equals 1. And then you've got x3 plus 4x4 plus 23x5 equals -9. And then x6 equals 16. Okay, so here's my system. Okay, so and then notice that I've only written down 3 of the equations. The row of zeros has no help. It is of no value, right? It's satisfied for any tuple, so it doesn't matter. It's basically inconsequential. Let's talk about what are called the pivot columns and the non-pivot columns. Okay, so the non-pivot columns are what? So you've got 2, 4, and 5. So these correspond obviously to x2, x4, and 5. Okay, these are what are called the independent variables of the system. These are the independent variables of the system. Okay, the non-pivot columns tell you what the independent variables are. The pivot columns are everything else, of course, 1, 3, and 6. So that's x1, x3, and x6. Okay. These are the dependent variables. Okay, the non-pivot columns are independent variables. The pivot columns are dependent variables. So if the system is consistent, okay, that's the first part. If the system is consistent, then the solutions are found by doing the following. Okay, so the first thing is letting any independent variable take on any real value. Okay, so the independent variables, so x2, x4, x5, they can be anything, any real number. Step 2, using your choice of independent variables, you have to derive the dependent variables. Okay, so hence the name, right? Independent, dependent. The dependent variables are derived from the independent variables. Okay, so let's go through this particular system up here and figure out how we would write the solution set for this. Okay, let me rewrite the system. So I've got x1 minus 2x2 plus 3x4 plus 5x5 minus x6 equals 1, x3 plus 4x4 plus 23x5 equals -9, and then x6 equals 16. Okay, just to remind ourselves here. So the dependent variables, the independent variables are x2, x4, and x5. So we're going to give those guys new names. So let x2 equal b, x4 equal d, and x5 equal e, right? Just nicer. The names that the symbols you would typically associate with scalars, b, d, e, a, b, c, those little lowercase letters, right? And so, and we know we're going to let these guys equal these, and we know that x6 is equal to 16. Okay, so we've got these two pieces of information. Let's go ahead and find x3. Okay, you got to remember, move your way up the system, right? So you start at the bottom and move your way up. That's what Gaussian elimination provides you with, that kind of easier sort of back substitution. So we've got x3 plus 4x4 plus 23x5 equals -9. And so I can just substitute, right? So x3 plus 4 times d plus 23e equals -9. And so that means x3 is just -9 minus 4d minus 23e. Okay, and so you might want to just note that. That's your x3 now. Let's find x1. So that's how we found x1. So to find x1, we would do the same thing. All right, so what do we have? We have x1 minus 2x2 plus 3x4 plus 5x5 minus x6 equals 1. Okay, so I can just plug everything in. So notice this doesn't have x3 in it. If it did, you'd have to plug this value in. Right, would make it a little more complicated, but so x1 is just x1 minus 2b plus 3d plus 5e minus x6, which is 16. Okay, and so x1 is equal to, all right, you can just rearrange, you can just kind of put this all on the other side of the equation, and you're going to get a 2b minus 3d minus 5e, and then it's 1 plus 16, so it'll be plus 17. Okay, and so there's your x1. Okay, and so that is that. And so then the solution set, all right, what's the solution set? Well, the solution set is, I can just rewrite all of these in the proper order. And so it's going to be a 6-tuple, and x1 is this big old thing. So 2b minus 3d minus 5e minus 17, that's your first component. x2 is b, x3 is -9 minus 4d minus 23e, x4 is d, x5 is e, and x6 is the number 16. There's your solution set such that b, d, and e are real numbers. Right, so here's your x1, x2, x3, x4, x5, and then x6 is always 16. Okay. All right, very good. Very, very good. Okay, now there's just one really quick little theorem here that I just want to throw out because we'll need it later. And if I don't do it here, there's no better time to do it. So, quick theorem. That we'll need later. Okay, and this is a fairly quick we're not going to prove it. I'm just going to state it, and probably leave it at that given the time. So let A and B, so let A and B be matrices for which the product AB is defined. Okay, if that's the case, then here's the theorem, right? If R is any row operation, then doing the row operation on the matrix AB is equal to doing the row operation on A and then multiplying that result by B. Okay, so this is a little strange, right? So if I have two matrices A and B and I multiply them together to get a new matrix AB and I do a row operation on that matrix, I'm going to get some other matrix, right? So maybe I take the first row times a scalar, add it to the third row, whatever. There's three row operations. Doing the row operation to the product AB is the same as doing the row operation to the matrix A and then multiplying that new matrix by B. It's a little bit of a surprising result, right? So if I perform a row operation on product AB, then the same result can be achieved by performing the row operation on just A and then multiplying by B. Okay. And so that's part one. Part two says, well, we can extend this to an an arbitrary number of row operations. So if R1, R2, ... Rn are n row operations, then, well, basically Rn times, the nth row operation performed on the n-1 row operation, performed on the ... second row operation, performed on the first row operation, all of AB, right? So doing a series of n row operations on the product AB is the same thing, results in the same final matrix as doing the n row operations on just A and then multiplying by B. Crazy, huh? Very interesting. Okay, so part two basically says we can extend this idea to a sequence of n row operations. Okay, and you can easily check this on a specific matrix, right? You can easily check this on a specific matrix. So let me give you a specific matrix you can check this on. This is by no means a proof, but it just shows you that, oh, indeed, it does seem to work. So let's say I have 1, -2, 1, 3, 4, 2 for my A matrix. And for B, let's have 3, 7, 0, -1, 5, 2. Right, and so I've done the work ahead of time. So AB is 8, 11, 19, and 21. Okay, so let's just define a row operation. We'll let R be the row operation. And what we're going to do is multiply row 1 by -2 and add to the second row. So this is going to be -2 times R1 plus R2 into R2. Okay, so you could do any of them. This is just one I arbitrarily chose. Okay, so let's do that row operation to AB. Okay, and so that's basically -2 multiplied by 8 and 11, added to 19 and 21. Right, so we're doing this kind of thing here. And so what do I get? I get 8 and 11, and then -16 plus 19 is 3, and negative 22 plus 21 is negative 1, right? So there's the result right here. Now what the theorem says is that I should get the same thing if I do this instead. The row operation to just A and then multiply the result by B. Okay, and so here's my A. So what do I get when I do a negative 2 add on to this? Well, I would get 1, negative 2, 1, and then that second row, I'm going to get negative 2 plus 3 is 1. Negative 2 times negative 2 is 4, plus 4 is 8, and then 0. Right, and that needs to be, that's A after the row operation, and then let's multiply it by B. And what do we get? We get 8, 11, and you can confirm this, 3, negative 1. Okay. All right, and so that's obviously the same, right? So in this case, R of AB is equal to R of A times B, which is exactly what the theorem stated. All right, very good. And I think that's where we'll leave it. The next section will be somewhat shorter. On the same vein, we're going to talk about a very similar related mechanism for solving systems called Gauss-Jordan row reduction. And then we'll also discuss what's called the reduced row echelon form. Right, and that'll be a shorter discussion than this one. This one had a lot of introductory material that we had to get into. So, all right, take care, and we will see you next time. Take care.